Good morning, good afternoon, good evening. What time is it? I don't know. But thanks for joining in again. And to burn something or not to burn something, that is the question. And the answer is yes, burn something and analyze what comes out. It's called a combustion analysis. So many organic compounds are hydrocarbon based and, well, almost by definition, carbon based. Hydrogen, oxygen, and hydrogen, carbon, often oxygen, comprise so many different compounds. And I think there's even a chamber to absorb nitrogen oxides as well. But the deal is we put pure oxygen in this side of the contraption. We put our sample we want to analyze in the first furnace chamber. Make it really hot. Basically decompose it or get whatever is in the sample to combine with the oxygen. That travels to the next chamber, which has a magnesium perchlorate or something that can absorb lots of water. We make sure we mass this chamber beforehand and mass it afterwards and decide how much mass it gains. And in the next chamber, we have sodium hydroxide or something that will gain or absorb the carbon dioxide, react with the carbon dioxide, also gaining mass, and weigh it before, weigh it after, and maybe even go on with another chamber to analyze for nitrogen oxides. But in any case, knowing the mass before and the mass after will allow us to analyze the water absorption for hydrogen, analyze the hydrogen in the original sample, analyze the carbon dioxide chamber for carbon in the original sample, and work around that to get even the oxygen in the original sample. Alright, examples of samples. 0.105 grams of an organic dye analyzed by combustion analysis to give 0.257 grams carbon dioxide, 0.035 grams of water. The compound is also known to contain oxygen. The molar mass is found in a different experiment altogether to be 108 grams per mole. Find the empirical and molecular formulas. Alright, let's try it. One of the bits of data we were given, 0.257 grams of carbon dioxide. Well, 1 mole of carbon dioxide is 44 grams. No big deal, that's no surprise. But check this out. This next conversion, kind of tricky. Isn't it true that 1 mole of carbon generates 1 mole of carbon dioxide because there's 1 carbon in each one? And with the oxygen that we're supplying, the oxygen makes the carbon dioxide, but the sample supplies the carbon. And then also, isn't it true, 1 mole of carbon is 12.0-ish grams of carbon. So lo and behold, I've, with a few simple conversion factors, determined what the mass of carbon is in my sample. Similarly for the water, take the mass of water that was generated. Water weighs 18 grams per mole, but two hydrogens come from or deliver one water molecule, H2O. So 1 mole of water, 2 moles of hydrogen. See them right there, 2 moles of hydrogen. And then the moles of hydrogen to grams of hydrogen. And lo and behold, once again, the mass of hydrogen. And unless I've made a calculational boo-boo, and I often do, I'm sure I'll hear about it later, did the total mass, 0.105 grams. Part of that must be carbon, part of that must be hydrogen, and if indeed there's something left over and it's only, and we're pretty sure otherwise that it's oxygen, we just subtract. Interesting. So here are my results in grams, and let me go ahead and change this back to moles. So 0.07 grams of carbon, 0.0039 grams of hydrogen, 0.031 grams of oxygen. Change grams to moles. Okay. So what? Oh yeah. So now just as if we were comparing, determining in percent composition or how much of a particular compound is a particular element, I take those moles and I compare them to the smallest number of moles of those three. So it looks like the smallest one is 0.00193 oxygen. Again, we're assuming that that means 1 oxygen. If it doesn't, then we're in trouble. We just have to fiddle with it a little bit, but in this case it does. So it means 1 oxygen, and hydrogen amount compared to the smallest number is 2. carbon amount compared to the smallest number of moles is 3. So lo and behold, my empirical formula, C3, H2O1, if you want to mention the 1. And that comes out to a molar mass of 54. Just by the way, FYI. But you know what? That's not enough. That's the smallest whole number ratio in my molecular unit, my molecule, my molecular formula. So comparing that 54 to the given 108, and again that was determined in a different experiment, I find there must be 2 empirical units in the total molecule. So instead of writing just this, I can go ahead and claim it must be 2 of these, 2 of these, 2 of these. Yeah. I've totally forgotten why I wrote that one there. I'll just erase it before I post the PDF. But alright, another example. Combustion analysis, hydrocarbon has 4.4 grams of carbon dioxide, 2.70 grams of water. Original sample, 1.5 grams. Looks like in this one we only have a simple hydrocarbon, no oxygen, no nitrogen. So I'm going to take the same thing I did, do the same procedure. 4.4 grams of carbon dioxide, grams of carbon dioxide and mole of carbon dioxide. Then the tricky part, but simple, 1 mole of carbon dioxide is 1 mole of carbon. Carbon, carbon dioxide, carbon, 1 carbon, 1 carbon, and 1 mole of carbon weighs this. Discover the grams of those 1.5 grams in that sample, 1.2-ish grams were carbon. And lo and behold, by subtraction, the rest should be hydrogen. But I'll just go ahead and do it anyway. 2.7 grams of water, 18 grams of water, 1 mole of water. 2 moles of hydrogen come from and or generate 1 mole of water. 1 mole of hydrogen is 1 gram of hydrogen. And lo and behold, this one plus this one, very, very close to 1.5. And if we care to, we'll go ahead and do it anyway. Grams of carbon to moles of carbon. Grams of hydrogen to moles of hydrogen. Compare each one to the smallest whole number. So this is the smallest one. Compare it to itself, you get 1, of course. Compare this one to this one, and of course you get 3. We're very close to 3. No, not of course. Is it obvious? This is very close to 0.3. This is very close to 0.1. 0.3 divided by 0.1 is 3. So indeed, that's the empirical formula. But that can't be the whole story. There must be something else because carbon likes 4 bonds. You couldn't just have CH3. CH3, that would leave the carbon deficient in its bonding, and the hydrogen can't multiple bond, so share extra electrons. So it could possibly be C2H6. That's, oh goodness, is this true? Oh my, I made a mistake. That's not uncommon, is it? Okay, forget that. Yeah. So I better change that before I post that. Not a big, so it's probably something like this, right? Or I could fix up my bonding here. I really would have C3H9. Yeah, right. And I can't have that too easily. Alright, so I'll erase that. Last example. 1 gram sample contains carbon, hydrogen, oxygen. Combustion analysis yields 2.5-ish grams of carbon dioxide, 0.65-ish grams of water. Given molar mass is 388. Oh my goodness, that's a heavy molecule. Find the empirical and molecular formulae. Sometimes the plural is formulas, formulae. So yeah, if you're brave, you'll pause the video now and do it yourself. But I know, who's brave around here? We're just lazy. We just want to watch it and get the answer. Wait time. You're pausing the video. You're working on this yourself. Voila, 5 minutes later, here's the answer. So change grams of carbon dioxide to moles of carbon dioxide. 1 mole carbon dioxide, 1 mole carbon. 1 mole of carbon, 12.011 grams of carbon. And voila, the carbon in the original sample. 0.65 grams of water-ish. Grams of water to moles of water. 1 mole of water, 2 moles of hydrogen atoms. 1 mole of hydrogen atoms. This is the mass. And the mass of hydrogen. Do some subtraction from 1 gram. Oh yeah, that was the total, wasn't it? I mean, the original was a 1 gram sample. Okay, so 1 gram sample minus the carbon minus the hydrogen gives us the oxygen. And now let's massage those a little bit. We'll take grams of each one. change it into moles, like we always do. The next trick is to compare each one to the smallest number, 0.015, and see what we get. And we're sad. The reason why we're sad is because these don't come out to whole numbers. Not even close. Not close to integers. This comes out to 1. Cool. But 4.68, 3.66. Well, see, thinking as simple of a fraction as you can. 2/3 is another name, is approximately equal to 0.66. And same story here, 2/3, 0.6. What is it? 0.666666 repeating for 2/3. But anyways, so now we have a simple fraction, and if we can multiply this and this and this by one integer to make everything a whole number, how about if I multiply all of it by 3? Take this times 3, take this times 3, take this times 3. And voila, I have the empirical formula. Add up 11 carbons, 14 hydrogens, and 3 oxygens, and you get 194. But you know what? That's not enough. The molecular mass from a different experiment was 388. So how many 194s are contained in 388? About 2. That's why sometimes we can't really trust all of our sig figs up here to say that all that's really necessary, but I carried them anyway. Because when you divide, you're just looking for approximate, very close integers. So, oh my goodness, that's a big molecule. Is that all I have? Yay, that's all I have. Thanks for watching, guys. See you in class. Have a good evening, morning, afternoon.